Alright guys, welcome to school. Previously we have been looking at taking the derivative of polynomials, which are a type of function. Today we're going to be talking about taking the derivative of rational functions, okay? So rational functions, an example could be 1 over x or 1 over 2x or 1 over 2x squared. So these are functions that have some sort of polynomial or some sort of expression in the numerator, okay? So with that in mind, let's go ahead and jump right into our material. Okay. One of the things that we sort of discussed previously was the definition. Well, we definitely discussed it, but we didn't use, instead of using t, we used x for the definition. So in some books, and this is worth mentioning, the derivative is defined as the limit as h approaches 0 of g of t plus h minus g of t over h. So in this case, they're just using t as the dependent variable. Another thing that I wanted to mention is that if you want to denote the prime of the function or the derivative, you can say d delta g over delta t, or you can use this, for example, this operator d over dt of g of t. Okay, so these are all separate conventions that people use in other textbooks, but for us we're going to use the definition of the derivative as f of prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, and I provided the alternate notation for that at the bottom. Okay. All right. We need to review because we're going to be dealing with rational expressions. So we need to review. We need to go back to the basics, right? If you wanted to subtract a fraction, for example, 1 over 2 minus 1 over 3, what you need is a common denominator, right? So here in the first example, you would multiply the first fraction by 3, 3 on top and 3 at the bottom, and the other one by 2 at the top and 2 at the bottom. So that way you would get 3 over 6 minus 2 over 6, right, equals 1 over 6. All right. For the second example, we did the same thing. Okay, all we did was 1 over 5. We multiplied by 9 on both the top and the bottom, and 1 over 9 we multiplied by 5 and 5 on the top and the bottom. And so by doing that, we get 9 over 45 minus 5 over 45. We get this 4 over 45. And I don't have to tell you that I did exactly the same thing for the third one. Okay, multiplied by 4 on the top, 4 on the bottom, and for the other fraction, 3 on the top and 3 on the bottom. And so that's how I got my 1 over 12. There is one easier shortcut that you need to do that, and that is that if you have, for example, if you have a 1 over a plus 1 over b, all you have to do to add the fractions is put the b first plus a, okay, over ab. Okay, so for example, like this one over here, 1 over 2 minus 1 over 3, put the 3 first in the numerator minus the 2 over the multiplication of both numerators, so 1 over 6. And that is exactly what we got for the first example, okay? Similarly, if you have 1 over 5 minus 1 over 9, you can just do 9 minus 5 over 45, okay? And 1 over 3 minus 1 over 4, 4 minus 3 over 12, you get 1 over 12. So make sure you check these results and you compare them back, and they're going to be exactly the same as the other method, okay? This is just a shortcut, so use that freely, but we're going to use this concept for our definition of the derivative. It just makes things a lot easier. One of the things I forgot to mention is this is 1 over a plus 1 over b, and all these are subtractions, but essentially you can use this this convention for adding or subtracting. Okay. Alright, so let's go ahead and jump right in. Alright, so let's take the derivative of our function at x equals 0. Okay, so we want to calculate f prime of 0 because our x value is going to be, for the point that we're interested, we want the instantaneous rate of change at that x value. So that's what we want to evaluate, that prime at 0. Again, what is our definition of the derivative? That would be the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so let's we do know what f of x is, but we do not know what f of x plus h is. So we're going to go ahead and plug in f of x plus h. So for every x, we're going to substitute x plus h. So here we're going to get 1 over 2x plus h plus 1. All right, and we can simplify this further because, you know, I really don't like those parentheses. It makes things a little bit harder. X plus h to look at. So we're going to do 1 over 2x plus 2h plus 1. All right, and so now we can use this expression to plug it into our definition of the derivative. F prime of x. Okay, so let's write it here. F prime of x equals the limit as h, let me erase that, as h approaches 0 of my f of x plus h, so that is going to be 1 over 2x plus 2h plus 1, okay, minus my original one, which is 2x plus 1, okay. Alright, and so here what we would do is we would divide everything by h. Okay, but since we have fractions already, I want to use something that is going to be easier to look at. Okay, instead of dividing by h, we are going to be multiplying by 1 over h, which is exactly the same thing as dividing by h. Alright, so now let's do this. Okay, so f prime of x equals the limit as h approaches 0, okay, of, here we're going to use our skill that we learned. We're going to grab this numerator and we're going to put it here. We're going to grab this numerator and we're going to put it over here. And then our new numerator is going to be the multiplication of both of those. Alright, so let's go ahead and change my color so I can do this. Alright, so we're going to do 2x plus 1 minus the other numerator, which is going to be 2x plus 2h plus 1, okay, over the multiplication of both of those, so that is going to be 2x plus 2h plus 1 times 2x plus 1. Alright, okay, so now what are we going to do? Oh, I forgot to also multiply by 1 over h. Alright, so now we're going to eliminate some of these terms. Alright, so let's go ahead and eliminate some terms. Here we're going to eliminate this 2 because we have 2x minus 2x. We're going to eliminate this 1 because that negative basically changes the sign. So in the end, you're going to end up with f prime of x equals the limit as h approaches 0 of negative 2h, because that was the only term that was not eliminated, over 2x plus 2h plus 1, 2x plus 1, and all of this is going to be being multiplied by 1 over h. Now here's one more thing we can eliminate. Look at that h here and this h here. Can we get rid of that? Of course we can. So let's get rid of this. And now we have, okay, we have f prime of x is the limit as h approaches 0 of negative 2 over 2x plus 2h plus 1 times 2x plus 1. Okay, and so what happens here, if we say the limit as h approaches 0, this 2h goes away because we simply substitute for 0 in that case. And so we end up with negative 2 over 2x plus 1 squared. Okay, now if we wanted to know f prime of 0, well, now we just substitute 0 for x, and you're going to get negative 2 over 1, so you're going to get negative 2. Okay, simply substitute 0 for x at the end. All right, now this was, it's going to get kind of messy for these expressions, so eventually we're going to need derivative rules, which make life so much easier. Basically, people kept doing these like formal definition of the derivative, and then they noticed a pattern with their expressions. So that's how they came up with like derivative rules. All right, but for us, we're learning calculus for the first time, so we're applying all these like formal definition of the derivative so that we get like more used to our concept. Okay. In the next part of this series, I'm going to be solving 2 additional problems of this nature, so that you have more practice and more of a conceptual understanding on how we're dealing with these rational functions. Okay. With that in mind, I hope to see you in the next part.